Okay. So we left off yesterday. We have one more example of trig substitutions that we want to do. And this is going to be about the most complicated case. We look at our problem and what do we notice? We notice that we have a a quadratic term underneath a square root. And so we've seen a lot of these examples. Remember our Pythagorean identities, we usually want to look for like a sum of squares or a difference of squares, where it's usually like a constant minus x squared or constant plus x squared. Sometimes there's often, that itself, that expression itself is underneath a square root. Sometimes it's in a denominator. All of those, when you see those types of forms, are dead giveaway that we want to try a trig sub. This case is a little different because we don't have a sum or a difference of squares. We have one squared term, but then we also have a linear term. And it is under a square root, and the square root, of course, is the thing that makes it difficult, right? If the square root wasn't there, just a polynomial, and we can integrate. And so whenever we have square roots, we know that taking derivatives and integrals of square roots just perpetually give us more roots, right? If we integrate, we would get something to the 3/2. Ideally, if we take a derivative, we get something to the -1/2. So it would be a square root in the denominator. And it would keep going like that, whether we keep integrating or keep deriving. And so integration by parts isn't quite going to work well, right? Integration by parts, we derive one thing, integrate one thing. And doing so might be a little complicated with this because of the square root. And actually, I don't know, you may want to try integration by parts with something like this just because of the quadratic underneath the square root. You might actually get a 2x out. But in any case, can't make a u sub because there's nothing outside of the square root that would substitute out the differential. So we can't make a u sub for whatever is underneath the square root. We can try a trig sub. The problem is that we've got to do some fancy manipulation. So let's work on completing the square. Why do we want to complete the square? So if you remember, actually here, let me use x minus h. All the way back from pre-calc, our vertex form of parabolas looks something like this. And the nice thing about that is, of course, we can identify the vertex. And in our case, we have a difference of squares. Something squared plus a constant or minus a constant. So it's always going to naturally be in a sum of squares or a difference of squares. And so what we can do is do that with the quadratic term that's underneath the square root. So just remember, you want to take your b term, your linear term, divide it by 2 to get 3, and then you square it to get 9. We don't want to change the expression, so we want to add and subtract, right? Same function, haven't changed anything, just manipulating the way it looks. And then these first 3 terms are going to form a perfect square, and that'll be x minus 3 quantity squared minus 9. So really what our integral is, in a little bit of a nicer form, is the square root of x minus 3 quantity squared minus 9 dx. And now what do we have? Now we have our difference of squares. Here, I'll say look for. And what substitution do we want to make in this case? This is going to be the substitution we haven't made yet. It's a difference of squares. However, which term comes first? It's our function term, right? If it is constant minus x squared or some function of x squared, we want to look for a sine or a cosine. In this case, we want to make a substitution along the lines of secant squared, let's use theta, minus 1. So function minus a constant. And again, how do we set that up? Well, what do we want, right? We want 9 secant squared minus 9. So we take that secant squared minus 1. We want to multiply it by this constant term so that the constants match. And what do we have? We have x minus 3 quantity squared minus 9. So this one's going to be a little bit weird in terms of our substitution. So our substitution we want to make is to set this x minus 3 squared, that whole quantity, equal to 9 secant squared theta, right? If I replace that x minus 3 squared with 9 secant squared, that's what we want. And now to figure out our substitution for x, we just solve for x. Secant to the 1 now, theta, and we take our square root and then add 3 over. So x is going to be 3 secant of theta plus 3. So it seems a little weird at first because we have that plus 3 and the minus 3 in the x. But again, we can just work it out from what we want in terms of the substitution, how we want it to look underneath the square root, and then solve for our x. And nicely enough, when we take a derivative, that plus 3 is going to go away. So it's not going to be a complicated thing that ends up in the differential or anything like that. So we will have 3 derivative of secant and secant tangent, and then d theta. Everyone got it? Okay, so let's go ahead and make that substitution, rewrite our integral. We have the integral of square root of x minus 3 quantity squared minus 9 dx. And now our substitution, our x minus 3 squared, we specifically set to 9 secant squared. And then our dx was 3 secant tangent. So then we got to do all the algebra here. 9, we factor out underneath the square root, gives us a factor of 3, plus that factor of 3 will give us a 9 in our constants. Then our square root will be secant squared minus 1. We've still got our secant and tangent. That's going to be tangent squared under a square root. Gives me another factor of tangent. Tan squared theta, secant theta.
Wouldn't the tan square become oh, never mind.
Yep, square root. And then, let's see, do we have any sort of nice substitution? Not quite seeing one. Do we want to use sines and cosines? This might be a hard problem to integrate. So let's just do some scratch work here. Let's take a look at the integral. What's going to happen when we have, so tangent squared sine over cosine, that's going to give us sine squared theta over cosine squared theta, d theta over cosine cubed, excuse me. And unfortunately, that doesn't work either because the odd one is in the denominator. Let's see, can we do another u sub? I think we could actually do a u sub here. It's going to get a little wonky. I think that's the best bet. I'm just trying to think of how to teach and kind of see this. I think we did have worksheets and there's homework exercises on doing all of these trig integrals, right? Different powers of tangent, different powers of secant. Unfortunately, you just got to do a lot of these. And eventually once you do enough, you start to see it. You start to be able to think and your brain will run through various techniques. So of course we converted everything into tangents and secants. I'm not seeing a u sub here, right? Usually our natural process after we get to this point is to do a u sub either for tangent or secant, but it's not going to work out too well, at least at this point. And why is that? If I make a u sub for tangent, well, the derivative of tangent is secant squared. So we don't have the differential in terms of secant squared. The derivative of secant is secant tangent. So I have one power of secant, one power of tangent I can use for the differential, but then I'm left with one power of tangent that isn't going to substitute out well with the u sub of secant. So that's not looking great. Same thing with sine. My thought process kind of went there as well. But again, usually we like to substitute out one power of sine or cosine with the differential. And since our odd power on those factors is in the denominator, it's not going to tie in with the differential. So this point isn't that good, but hopefully at least somewhere in that thought process, something popped out at you a little bit, namely when we tried to do a u sub for secant. So this one's a little tricky. When we did a u sub for secant, we have secant tangent as the derivative. And nicely enough, we at least have this here. I'm going to write this as d secant theta. All right, derivative of secant theta is secant tangent d theta. And moreover, what else do we have in the problem at this point? We have secant squareds minus 1 over here. So let's try this. Here, a u sub will work, at least in terms of the substitution. We'll have to check it, go through our thought processes to see if it will actually help and make our integral easier. And again, this is very common for the process of doing integrals. Sometimes you got to guess and check. Your brain goes down one route, your brain checks another route, and sometimes you keep hitting walls, and then hopefully eventually you find the process or find a good process somewhere along the lines. So let's go ahead and rewrite that. And let's go ahead and make our u sub now as secant of theta. And when we do that, we have 9 times the square root of u squared minus 1 du. And unfortunately, I think that's just getting us back to where we started, isn't it? Ah. So really all we're doing is shifting this, right? We have something squared minus a constant once we solve for it. So this integral may not work out. It might involve using more fancier techniques of integration, either doing an integration
Someone suggested to use an integration by parts.
Yeah, an integration by parts might work out for this. But in any case, I'm going to leave it there. So the main point I wanted to illustrate with this problem was completing the square. So I stole this problem from a previous semester's notes. Apparently wasn't a great problem to integrate. The key point was that sometimes when you have these linear terms, you have to complete the square. So that was kind of the main point I was trying to teach. Hopefully everyone at least picked up on that, on how to complete the square. And then when you get these vertex form parabolas, you can then make that substitution in similar ways we have been doing. On test quizzes, of course, the problems will be much more worked out so that if you have to do the integral, it will be doable. Okay, so I just don't want to spend too much time on that since we have covered a lot of these trig subs. Wanted to go over that, completing the square method, of course, using a secant substitution as well. And then doing the rest of the integration. Usually the problems will work out much more nicely than this one. So to save a little bit of time, let's go ahead and move on because we want to learn our newer technique today. And our newer technique is partial fractions.
For that last one, I think what you do is you take the tan squared theta and you make it sec squared minus 1, and then you multiply it out. So you have sec cubed x minus sec x, and then you integrate those both separately.
And then you get tan squared, then you've got secant cubed.
And you've got secant cubed x minus the integral of secant x, and you can do those.
There you go. Yeah, we can write that out real quick. Thanks for looking at that. And again, this is exactly what you have to do. Your brain goes down different paths for doing these integrals. And then sometimes you hit a wall.
That one wasn't my brain. That one was Wolfram Alpha. So.
That was Wolfram Alpha. Ah, nice. Then you have that technique. Yeah. So if we have 9 tangent squared, you turn the secant squared minus 1 times secant. And then you get in that integral of secant cubed minus secant, which again are hard integrals, right? We talked about the tricks for those and having to do this fancy multiplicative factor. And then you can finish those guys out. But yeah, so thanks for that. I didn't want to spend too much time on that. Of course, sometimes when you're doing homework as well, some of these do get quite lengthy and you do get to spend the time. But for the sake of class time, let's go ahead and move on to partial fractions. Let's see, where's my example? So partial fractions are process. The big idea is we are doing common denominators in reverse, essentially. Right, you're Calc 2 students now, so you remember if I'm adding rational expressions, the way we would add rational expressions typically, we find common denominators, add them together. Now what we want to do is usually we'll have rational expressions we want to integrate. Which are hard, right? We've seen integration by parts. That's our fancy trick to do the multiplication rule in reverse. But as I kind of mentioned yesterday, we don't have a quotient rule in reverse. So when we're given quotients underneath an integrand, our integration techniques can be a little tricky. We almost have to check everything. U subs work for those sometimes, trig subs work for those sometimes. And now we're going to learn partial fractions. So we're given a rational function under an integrand, and
use reverse chain rule as well for some of those.
Reverse chain rule, that's U sub essentially is what we're doing there, is the reverse chain rule. So sometimes that works for rational functions we want to integrate. And then in this case, what we're going to do is factor the denominator. And then split the fraction into a sum. Right? We're doing the opposite of finding a common denominator. Instead of adding different rational expressions and then combining them into one, we're given one rational expression and splitting it into a sum. So let's practice with that. Let me see if we have an easy one we can start with. Let's just go through the process real quick. So this is without integration. So for example, let's just do something fairly easy. Let's say we've got 3 divided by, let's pick something that factors nicely. Let's say x squared plus 2x minus 15. Our first step is to factor the denominator. So we've got x plus 5 and x minus 3. Then what we want to do is write it as a sum of different factors over those individual factors of the denominator. And I'll explain a little bit more about where these factors come from and how we manipulate them, because they're going to change. These expressions that appear in the numerator depend on what we see in the denominator. And actually, let's explain that now. So since we have linear factors in the denominator, let's get some more space. So since factors are linear in the denominator, right, degree 1, we want to put generic polynomials of one less degree. In the numerator. And we'll try to get to some examples like that. I'm not sure how much time we'll have today. It looks like we still got another hour of class, and then we'll have time on Monday to do partial fractions as well. I've got a lot of different examples, and the way I try to do my examples is to build up difficulty. So we're starting with an easy case. We've just got a basic quadratic, which is going to factor into linear terms. And so we want to be able to write it as something like this, where I have my linear terms in the denominator, and then the numerators are always one less degree than whatever our denominator is. So if we have a degree 1 in the denominator, we just want constants in those numerators. And now what we want to do is try to solve for what A and B need to be, right? If we tried to find a common denominator, we would have A times x minus 3 over x plus 5, x minus 3, plus B times x plus 5 and this expression should be the same thing we started with, right? We're not trying to actually change our expression, just change the way it looks. And we see by trying to find our common denominator, right? Or of course, those factors give us that same common denominator that we had, that we started with. And so when our fractions are equal when both the numerators and denominators are equal. So if the denominators are already equal, all we have to do is now solve the equation of this guy. So we've got A times x minus 3 plus B times x plus 5 equals 3. And there's two ways to do this. There's the proper way, and then there's the fast way. I'm going to teach you the fast way first because it's the one you're going to want to use the most whenever you can. It will save you a lot of time. So what do we have? We are equating two polynomials, ideally, right? If we could multiply everything out, collect our like powers of x, collect our like powers or our like constants, and put those in one term. And then I would have a polynomial on the left equal to a polynomial on the right. Polynomials are equal whenever all of their coefficients are equal. So that would be our typical traditional way. But we can also think of it as, well, polynomials are equal if they are equal for every value of x, right? We still have x's here, but we're not solving for x. We're solving for our constants that define this polynomial. So if the polynomials are equal, they're equal for every input value of x, meaning we can choose nice values of x to simplify things. So again, we've got equality on polynomials. Well, that means they have to be true. This equality has to hold if x is, say, equal to 3. Why am I choosing x equals 3? What's going to happen to this term? That means our equality is going to hold when x is 3, and when x is 3, we will get this statement. our a term drops out, and we get 8 times b is 3. So b is equal to 3/8. Likewise, we can choose x equal to -5. And why does that help us? We will have a times -8 plus b times 0 equals 3. And we see that now a is equal to -3/8. So all in all, what do we have? We have that 3 over x minus 3 x plus 5 is equal to, so a was negative, and a corresponded to the denominator of x plus 5, and then our b was positive. So because our a and b ended up being fractions, I just keep them outside. You can multiply those through if you want. But so why did we do this? Our typical next step would be something like if we had to integrate something like this. Right? If we just had to integrate this rational expression, well, you could try a trig sub. Now, knowing the techniques of completing the square, we could complete the square in the denominator and try a trig sub. But as we just saw, sometimes those trig subs can get a little hairy, especially at the end when we're left with trig integrals of different powers of trig functions. So partial fractions, if you get used to it in solving these systems of equations for a and b, it's a little bit more algebra from the get-go, but the result is really nice. Now we have just linear terms with constants. I can integrate, if we wanted to integrate this, it's the same as the integral of this term, since those expressions are the same. And integrating these guys is easy. It's just going to give us some natural logs. So let's try one of these. Let's see. I think we may want to make a note about, let's see, what was I just thinking of? I thought of something I wanted to mention, then I was talking about the end and then forgot what I was going to say. In terms of the choice of A and B, we'll see a lot of examples, and maybe I'll make notes as we go, because the A and B and how you set these up, it's going to change, and there's different caveats, but I think it's best to kind of just learn those techniques as we go. The fundamental theorem of algebra. That's what I wanted to mention. So fact. This is the fundamental theorem of algebra. So this is a little bit beyond the scope of this course. It's just a fact you guys have to know, but hopefully maybe depending on how far you guys are getting in your studies, I don't know if any of you guys are actually applied math majors. Maybe you'll get into it and understand how the proof goes. But it basically states that every polynomial with real coefficients can be factored into irreducible factors of degree 1 or 2. So what is that saying? When we see these expressions, again, they're going to be rational expressions, which means we're going to have polynomials in the denominator. It means that no matter how high or what degree of a polynomial we have, we can always break it down into factors of degree 1 or 2, meaning each of these factors that we want to split it into is either a degree 1 term or a degree 2 term, which is nice, right? That's really nice for this process. It really simplifies things. We're not going to have cubes. We're not going to have degree 4 and worry about weird, numerators that we have to solve out a bunch of constants for. It makes things really nice, especially with degree 1 terms. We can integrate those very easily. In degree 2 terms, we now know a lot of different techniques for. So if it's irreducible degree 2, we can look for U subs. We can do integration by parts or trig subs for. The only thing that's also going to come up is if we have a higher degree, the only way we can have a higher degree in the denominator is if the factor has a higher multiplicity, meaning it's a linear factor, but then it's like x plus 5 quantity cubed or something like that. And we'll see how to deal with those. Again, those aren't too bad because those are easy to integrate. If it's a linear term all to the even 10th power, we can integrate those pretty easily. And you guys learned basic U subs for all that last semester. Okay, so let's do some more examples with these. Let's see. So let's do the integral of 5x minus 4 over 2x squared plus x minus 1 dx. And I guess I should mention, what do I mean by irreducible factors? I'll explain that as we come. Our second example will be something along those lines. Irreducible factors, well, linear, I can't factor that anymore. What do quadratics look like? Think about it just in terms of complex roots, imaginary numbers. So we can have quadratic factors with pairs of imaginary numbers as roots, so you can't factor them anymore over the real numbers. Okay, so our first step with this guy, we're going to look to factor the denominator. So let's do that real quick. We've got 2x and we've got a minus 1. So it looks like 1's going to be negative. We've got a positive linear term, so we want that guy to be positive, this guy to be negative. So we'll have 2x minus 1 times x plus 1. And then all we want to do is a over 2x minus 1 plus b over x plus 1 has to equal our term here. So I'll put a little box there to sort of box out some of the scratch work we're going to do. That is the one thing about integration by parts, is that it's kind of a lot of scratch work before you actually get to doing the integral. So it's good to keep your work organized. And what's going to happen when we find a common denominator, we'll have a times the other denominator plus b times the opposite denominator. And then that's going to be the numerator if I combined those fractions. And so that's going to equal the numerator on the right. Everyone follow me on that step? So again, because it is kind of a lot of scratch work, I like to go through some of the steps quickly. If you're not comfortable with doing the algebra, just do it in the steps we did on that previous one, right? You can refine a common denominator with those terms, and then you'll see that the numerator should give us this expression when we equate them. And so first thing we're going to do is look for our fast method. Can I find easy values of x. We have an equation of polynomials again. Polynomials will be equal for all values of x, including when x is equal to -1. So when x is equal to -1, this term, the a term, is going to be 0, and we will have b times -2 minus 1 equals -5 minus 4. And so we will get -3b equals -9. So our b is 3. Easy enough. Our other x value, that's going to be nice to choose. So we want to look to kill one of the terms. If you haven't picked up on that, that is our choices of x. We want to look for zeros of these factors. So in this case, we should pick something like x is equal to 1/2. Not a terribly nice number. We've got fractions involved. Might make some of our arithmetic a little difficult. So our a term, we will have 1/2 plus 1. So we will have 3/2 a. B term, when x is 1/2, going to vanish. And then so 3/2 a is equal to 5/2 minus 4. So let's work that out real quick. Let's see. So 4 is 8/2. So -3/2. And then times 2/3. Nicely enough, our a is going to be -1. So I'll close that little box for our scratch work. And now let's rewrite something. If I ever flip pages, also, by the way, if you guys haven't finished writing, please speak up. Let me know. I'll try to pause at the end. I know you guys are lagging a little bit with writing down all the notes. All right, so we have our integral of 5x minus 4 over 2x minus 1 times x plus 1 is equal to the integral of a was divided, had a denominator of 2x minus 1. So we had a -1 over 2x minus 1 plus b had the denominator of x plus 1. So that's going to be 3 over x plus 1 dx. And now, pretty easy integrals. This one has a 2 in the denominator. There's some constants we got to work out. You can do a u sub for this guy if you want. This guy should be pretty straightforward. And I'm going to go ahead and do some just basic, like, chalkboard math. I'm going to split that integral into 2. So we do have 2 integrals here. We can do each one individually. The nice thing about linear factors is that it's always going to be whatever that constant is times the natural log. And we needed 2x minus 1. And if we did a u sub, we would reverse our chain rule that we would get for this factor of 2, which would give us a factor of 1/2 plus 3 times natural log x plus 1. And then, of course, plus your constant. Questions on that guy? All right, let's take a quick break. We've been going for about an hour now, and then we will take a look at some more examples once we get going again. Okay. So we're doing partial fractions. So far, does everything make sense to you guys? This is actually like easier. In my opinion, I think partial fractions is easier than trig subs. It's just that you kind of need trig subs every once in a while with certain partial fractions. So you do have to do trig subs first in terms of the learning scope in Calc 2. All right, so let's take a look at some more examples. And let's get a little more complicated. Let's do one. Let's see, I've got 2x squared minus x plus 4 over x cubed plus 4x dx. So our step one, of course, is to factor the denominator. May want to look to factor the numerator too, but numerator is not as important. So we can factor into x times x squared plus 4. Numerator, let's keep the numerator as is, actually. Sometimes it helps to factor the numerator if you can cancel out one of the factors. And so maybe if you just eyeball it real quick. I don't know how well that would factor. We could split the 4 into 4 and 1. I don't even know if it would. Doesn't look like it will. And it doesn't look like we'll get either of those factors. So we can't simplify. We can't cancel anything out of the numerator. But we factored our denominator once. And now the question is, can we factor this guy? So let's do a little aside here. Just to remember some pre-calc, how to tell if we can factor a quadratic. And case in point, we've got x squared plus 4. Well, if we tried to factor it, one, you could try to write it as a difference of squares. However, it's really a sum of squares. So for those of you guys who have had complex numbers somewhere in high school, I know sometimes they teach it at least what they are. The roots would be 2i and negative 2i. The other thing you can do is check the discriminant. What is the discriminant? It's this guy. So hopefully everyone remembers the quadratic formula, right? And then our square root of b squared minus 4ac is our discriminant. So if b squared minus 4ac, and actually we don't even need this square root. We're really just checking b squared minus 4ac. If it's negative, it's irreducible. We cannot factor anymore. If it's positive, we can factor, and sometimes we would have to use fancy techniques like the quadratic formula to find the roots. So our b squared is 0, right? Minus 4 times a times c. So negative 16. So a negative discriminant means the roots are imaginary. So we cannot factor that anymore. And so now what we want to do is write our rational expression in terms of splitting the factors of the denominator. X is easy. Just a degree 1 polynomial, which means the numerator needs to be degree 0. So just a constant. It's these factors that we're going to have to change a little bit now. So this is a degree 2 polynomial, which means the numerator could potentially be a degree 1 polynomial. So we always do one less. So a degree 1 polynomial is a linear polynomial. In generic constants, it would look something like this: bx plus c. Okay. And so now we want to reverse engineer, try to figure out what our constants are, a, b, and c, that will give us the same numerator if we were to try to find a common denominator here. So we'll have a times the other denominator, x squared plus 4, plus bx plus c times x equals 2x squared minus x plus 4. And again, if you're not following along, just go through the reverse process, right? If we were given this and wanted to find a common denominator, you would end up with this guy in your numerator. So check that on your own. And then, of course, we want to set the numerators of our rational expressions equal to each other. And here's the tricky part. So now we want to use this fast technique for solving for the constants, but we're actually not going to be able to do it for all of them. One factor stands out. We can use it for some. So if x equals 0, we will get 4a plus, so when x is 0, this whole term will be 0. And of course, we'll get the constant term on the right. And so nicely enough, we can solve for a. But now what's going to happen? So when we have one of the constants, we can always substitute that in and rewrite our expression. So really what we have is x squared plus 4, since we know our a was 1. Bx plus c times x equals 2x squared minus x plus 4. And so if we wanted to find b and c, we could try to check other powers of x, or excuse me, other values of x. But what would happen? Can I get this term to vanish? We can't, right? The factors of this guy were imaginary. It has no roots. There's no values of x that I can put in here to make this whole expression 0. So what we have to do is to do this the brute force way, so to speak. So we're essentially just going to multiply everything out and then equate the constants for the powers of x. So nicely enough, since we found a, we can take this polynomial and subtract it over to the other side. So on this left side, we'll have bx, and I'm going to go ahead and distribute that power of x. Bx squared plus cx is equal to x squared minus x, and then the 4's canceled out. So not too bad looking. And now this one didn't end up being too bad. Sometimes the algebra here can get a little hairy, which is why I definitely recommend doing the fast way first. This saved us a lot of time being able to solve for this a value. because now all we have to do once we've done the arithmetic, the algebra, is equate the coefficients for the corresponding power. So, right, this is an equals, two polynomials are equal when the coefficients are equal. So this tells us that B has to be 1 and that C has to be -1. So we've got all our constants. Now we just plug them in and rewrite it. So let's see what we got. We were doing integral. We've got 2x squared minus x plus 4 over x times x plus 4, x squared plus 4 is equal to now the integral. Our a constant was 1. I'm going to go ahead and split up the sum over the integrals. We had bx plus c. B was 1, c was -1. So we've got x minus 1 over x squared plus 4. And now we just solve. So first one's easy, gives us a natural log. Then this guy, how do we do that? So nicely enough, and this doesn't always work out. It depends on what this constant here was. Sometimes this constant, this b constant, could have been 0. So if it were 0, we would get something like 1 over x squared plus 4, in which case you'd have to do a trig sub, look for a tangent substitution. However, since we do have a linear term in the numerator, we should now be able to do a u sub. And actually, let me correct myself here. It looks like we're going to have to do both. So let's go ahead and do that first one. Let's get our natural log of x. We can do that integral, keep it off to the side, plus we have the integral of x over x squared plus 4 minus the integral of 1 over x squared plus 4. So I just caught myself there while explaining that. If we wanted to do our u sub with something like this, right, our u is going to be the denominator. And we see that because the du will be a linear term, something like 2x dx, and we can substitute that out in the numerator. The problem was that constant, right? We cannot substitute out, we cannot add and subtract constants to a differential. It doesn't work. So what we have to do is split it from the get-go. And now with this guy, we'll do our u as x squared plus 4. Our du is then 2x dx. And so our 1/2 du is x dx. So we've got natural log of x plus the integral of 1/2 du over u, or 1 over u du, minus, what do we need to do for this guy? We've got sum of squares. And so we want our x squared to be 4 tangent squared theta. We solve everything out. And so we've got our integral of, here, let's go ahead and write it as 2 secant squared in the numerator, divided by 4 tan squared plus 4 d theta. So I'm doing both these integrals at the same time. Bit lengthy of a problem, but just about done. So what's this guy end up being? When I factor out the 4, we've got a 2 in the numerator as well. We'll have a 1/2. We've got secant squared in the numerator. Tangent squared plus 1 is also secant squared. So those will cancel. So we've just got our integral of theta. Let's go ahead and back substitute our u. This is the integral of theta, or d theta, which will give us a theta. And then lastly, we just need to back substitute that guy. So it should give us what, 1/2 arctan of x over 2. So all I did was solve for theta from up here. Divide by 2, take arctan of both sides. Any questions? Okay, so it looks like we got about 5 minutes. I don't really want to get another problem started. There's a couple more problems we need to do. We need to take a look at, one, what's going to happen with these multiplicative, or when we have multiplicities of the factors greater than 1. Right? So far, this was an x squared plus 4, but that quantity was to the 1. Same thing with that factor. And in other factors we've seen, we saw these examples of like 2x minus 1 and x plus 1. We could just as well have the quantity x plus 1 squared or cubed. So that's going to change things a little bit. There's different ways of doing it. You actually don't need to change much. Only you can sort of operate under the same principles we have been operating, namely that these, when we set up our partial fractions, the numerator, the generic polynomials we are sticking in the numerator, just need to be of degree 1 less than the denominator. So we'll talk about that on Monday. We'll also talk about, well, what happens when the degree of the numerator is bigger than the degree of the denominator. Excuse me. Right, excuse me. We've cooked these up specifically so that the numerator is 1 degree less than the denominator. This allows us to do things like u subs and trig functions. But if the numerator is a higher degree than the denominator, then we actually have to do everyone's favorite thing, I'm sure, which is polynomial long division. So if you remember that way back from pre-calc, it's a pain. This is why I joke that it's everyone's favorite thing. I don't think those problems will come up a lot. And as we already kind of saw, since partial fractions start to tie in together almost every other technique of integration we've learned so far, the problems can be a bit lengthy. So to make them even longer, if the degree of the numerator is bigger than the degree of the denominator, you first have to do long division, then do partial fractions on your remainder term, essentially. So we'll see that on Monday. We'll try to whiz through an example, try not to spend too much time. But for the last couple of minutes, let's go back and review what we did with solving for these constants. And I want to just formally work through the official way, so to speak, the tried and true, I guess we should say the what do we want to call it, the error proof way of doing this. we saw when we were solving for these constants, let me find the page here. Yeah, let's just go back over this previous example. When we want to break down a rational expression into a sum of different rational expressions, of course, we've set up our generic constants, and then when we find our common denominator, we look for a method like, or we look for our numerators in an equation like this. And then we look for factors of x to see if it'll simplify things for us. That will kill some of the terms. And we saw that it doesn't always work. Sometimes we don't have constants that I can just plug in for x and that will annihilate everything. In this case, this occurs when we have imaginary roots, when one of the polynomials is a degree 2 that's irreducible. And so it is possible to have all of the factors in the denominator as irreducible degree 2 polynomials, in which case we're not going to find any of these nice x values that will simplify things very nicely for us. So what do you do in that case? Let's go through that real quick. Hopefully it won't take too long, only a couple minutes here. Let's just rewrite this equation and do it the official way. So we've got a times x squared plus 4 plus b bx plus c times x is equal to 2x squared minus x plus 4. And we want to solve for our constants, a, b, and c. So the official way of what you want to do is just multiply everything out and then combine your like powers. We want to write this left side as a nice polynomial, something times x squared, something times x, plus a constant. So we'll have ax squared plus 4x, or 4a, excuse me, plus bx squared plus cx equals 2x squared minus x plus 4. So our x squareds, we will have a plus b as our factor of x squared. So essentially, I'm just putting the squared terms together, factoring out the x squared. We put the linear terms together. We only have one, plus cx. And then we put our constant terms together. We've got 4a, and that's our only constant term. And so now, once we have our nice polynomial over here, constant times x squared plus constant times x plus another constant, now we just equate each coefficient. So this tells us that a plus b equals 2. Our linear term, c, has to equal -1, and 4a has to equal 4. Now, this equation was fairly simple. With the last way we did it, we were able to kill one of the factors, and then we saw, solving for b and c after that weren't too complicated. And even here, nicely enough, we immediately can find c and a pretty quickly, and then use those to find b. But you can imagine that sometimes there's different expressions on the linear term, different expressions on the constant, right? This could have been, an a plus c. This one could have been 4a plus 3b. And you would get these systems of linear equations. So a little bit of a review on those. You got to remember how to solve those. Usually there's some easy substitution methods. In this case, of course, we have our c. We can solve for a very easily as well, and then use any of those to plug back into the other equations for the other unknowns that we're looking for. Does that all make sense? Okay, so you might see some of those examples in homeworks or anything. Homeworks or WebAssign. Feel free to talk to me during office hours or after class if you got questions on those. again, because our lectures are, we have an hour and a half, but there's going to be a lot of examples that come up that I'm not going to be able to cover everything. So I'll try to cover as much as I can and all the techniques I can. Anything else that comes up that's a little more fancier, feel free to talk to me in office hours. All right. Have a great weekend.
Thank you.